Hello again, Algebra 2. So here we go, 10.2, independent, dependent events. So independent events are basically events that are not affected by whatever came before. When you toss a coin, it doesn't matter if you got a heads or a tails on the previous toss, you're still going to get a 50-50 chance, each outcome equally likely. That would be an independent event, all right? Previous events do not affect it. However, if you're, say, pulling marbles out of a bag or candy out of a bag and you do not replace what you chose, then the next time you reach into the bag, it will be affected. So especially with these kind of events where there's without replacement, those are called dependent events. And we're going to look at how probability is created during these, whether it's independent or dependent. So the first thing we want to be able to do is just identify whether it's independent or dependent. So if you are running a race and the probability of finishing in first, second, or third, is that independent or dependent? So think about that before I write down an answer. What do you think? Well, it should be dependent because if you come in second, that means someone else already came in first. So it depends where you were in the line. Then we have choosing a pizza size and a topping for the pizza. Does the size affect the topping you choose? And this is where you have to kind of be a little bit, don't try and be all analytical and practical. There is no actual causal relationship between the size and the topping. So we call that independent. Some people might say, oh, well, I don't want this topping on a really big pizza, but that's not the concept. This is sort of theoretical. There's no causal relationship. Then we have raffle tickets. They're placed in a jar. 3 tickets are then selected, one after the other, without replacing the ticket after it is chosen. So if you did not replace the ticket, is this your ticket going to be dependent or independent? Well, since it was not replaced, it's going to be dependent, because that would be kind of silly. If everyone replaced their tickets, everyone could win the raffle. Then we have the 232 members of the freshman class all vote by secret ballot for the class represented to the student senate. So ignoring, the concepts of peer pressure and all that, voting should be independent. You can vote any way you want and no one needs to know how you voted. Okay? So hopefully that makes sense, the distinction between independent and dependent. Now we want to go through and look at how do you find the probability. So if we have independent events, where one event does not affect the other, this is sort of like your counting principle. If the 2 events are independent, then the probability of A and B is going to be their product. So for instance, if I'm going to toss a coin twice, the probability of heads and then heads is going to be 1/2 times 1/2. And you can look back on 10.1 where we looked at that sample space and there was only 1 out of the 4 possibilities where both were going to be heads. Here we have a jar contains 15 red marbles, 17 yellow marbles, so that gives us a total of 33 marbles in our sample space. You randomly draw 1 marble from the jar and then you replace it before you randomly draw a second marble. So it's that replacing it that is going to make this independent. What is the probability that you draw a yellow marble first and a red marble second? So the probability of yellow and then red. Well, that's going to be of the yellow, we're going to have 17 out of the 33 multiplied against, then we pull the red, since there's still 33 marbles in the bag, you have the probability of choosing 15 of those. And we would then multiply that together, which is going to be a huge number, so I'm not going to multiply it right now. Another example, you spin the spinner shown right here to the right, and you spin it 2 times. What is the probability that the spinner stops on an even number, the first spin, followed by an odd number on the second? So the probability of even number, and then, I like to put the then, an odd number. All right, so let's look at this. Even numbers, we've got ourselves 6, 8, 12. We have 3 of them out of 8 spaces. So 3 out of 8 would be an even number. Then when we go to spin it that second time, there is no causal effect on what came previously, so the remaining are going to be 5 out of 8, and that would give us 15 out of 64. That's the probability of those 2 events occurring. So we looked at independent is just the product of the 2 events happening one after the other. What happens when the 2 events are dependent? It makes sense that the second one is affected by the first, so it should change its probability. Well, the way we look at this is probability of A and B, knowing that they are dependent, is going to be the probability of the first event, that's just calculated as it normally would be, times the probability of the second event given, that's how we represent this notation-wise, the probability of the second event given we know what happened on the first event. Probability of B given A happened. All right. Now, later on, we are going to look at this relationship, and we're going to find the probability of B given A. I can rearrange this because this is just a relationship. If I isolate this part, then what I'm doing is that's going to be the probability of A and B over the probability of A. That's going to come a little bit towards the bottom of this page. So just realize this is a relationship. If I'm looking for any one of those, just the probability of A, I would then isolate that. Okay, well, let's start off with the simple version. There are 5 tiles with the letters A, B, C, D, and E in a bag. So we have 5 items in our bag. Tiles, I guess. You choose a tile without looking at it and put it aside. And then you choose another tile without looking at it. Find the probability that you chose a vowel followed by a consonant. So we want to find the probability that you chose a vowel and then a consonant, and again, this is without, because we put it aside, it's without replacement. That means the second time you go into the bag, it was affected by the first time you went in the bag. So we start off, the probability of a vowel. So we have A and E are our 2 vowels. So that would be 2 out of 5. That's the probability of A. Now the probability now of getting a vowel, there are still 3 B, C, D, 3 vowels in there, but there are no longer 5 tiles. We lost a tile. So this sample space was affected. The sample space went down because we did not put back that initial tile. So we still multiply the 2, but we had to calculate the probability based on the fact that the tile was without replacement. So when I go to do this, we are going to get 6 out of 20, 6 out of 20, which is going to reduce to 3/10. That would be the probability. Now let's see what would happen, the probability that you choose a vowel, so probability of, again, choosing a vowel, and then another vowel. And again, we're not replacing, so that these are dependent events. So we started off with only 2 vowels in the bag, and we choose one of them. The probability of that happening is 2/5. Well, now that we know we chose a vowel, there's only one vowel left, so the next probability will be 1/5. Sorry, I just made a mistake there. Hopefully you caught that mistake. Where's my back button? 1/4, because we have one less in the bag. We have one less vowel and one less tile. That is going to give me 2 out of 20, which is then 1/10. All right, so you're just calculating each probability separately, but you have to consider what came before. All right, now let's look. I'm trying to move this so that I can, we can see this table over here. Let me pause for a sec. Okay, so finding the conditional probabilities. This is a dependent concept. It's conditional on what came before, or conditional on other probabilities. So first thing we're going to do is, how do we use a table to organize some of this information? So we have a quality control inspector who's checking for defective parts, and this is showing the result. So you have items that are defective that pass the test, and items that then fail the test that are defective. And you would hope that that failing would be the larger number, because you don't want defective items to actually be passing through, but it happens. Also with non-defective, most of them passed, 208 of them, but 9 of them did fail. So we look at this and we want to find the probability that a defective part is passing. So what this translates to is we're finding the probability of something passing given we know it is defective. So we're looking at a subset of all the items that we have looked at. This is where we're going to use sort of that simplified equation I wrote up above. So sort of like the probability of B given we know it's A. So the probability of passing given we know it's defective. So we're only looking at then the defective row. So there are 5 that passed out of the total defective items, which is 29. And that would be the probability that you pass given we know you're defective. Not you, but the item. Okay, find the probability that a non-defective part passes. Okay, so this is going to be the probability that it passes given we know it's not defective. So the subset we're looking at now is down here, and that would be the probability of it passing is going to be 208 out of all the ones that pass, and that's going to be, so you have to find, these are called your marginal frequencies, the totals at the end. So, oops, I did that wrong. 217 would be our total. So the probability that it passes given it's not defective is 208 out of 217. Tables, which we're going to look at more in 10.3, are a great way to kind of organize the information for these conditional probabilities. But let's look at a situation where it doesn't come to you in a table. So I want to remind you, we're utilizing now this concept of B given A. We're looking at the conditional probability of B happening given we know A happened. That equals the ratio of the probability of both happening over the probability of A. Because A is the big event, B is then part of that. So let's see. At Starbucks, we have 80% of the customers order coffee. That is going to be our event A. We know 80% of the people that come in order coffee. Of those 80%, 15% of them order both coffee and a pastry. So this is our event A and B. They're ordering coffee and pastry, but those are a subset of the people that ordered coffee. So what is the probability that a customer who orders coffee also orders a pastry? So the way we read that is the probability of ordering a pastry given we know you ordered coffee, what is that probability? So that is the probability of coffee and pastry divided by, because that's a subset of the people that just order coffee. So when we look at that, so how many ordered coffee and a pastry from the total people that ordered coffee? That was 15% out of the number that order coffee when they go in, because some people just go in and get water or something, I don't know. And then when we calculate that out, you would get 0.1875, which comes out to be 18.75% of everybody. That is how we would calculate that conditional probability. Okay, so again, sometimes it takes a little bit of practice in reading these. So remember, 80% ordered coffee, only a portion of them ordered both coffee and a pastry. So we want to find what's the probability that if you did order a coffee, you will also order a pastry. So we're just looking at then those people who ordered coffee, not all customers. All right, see you guys later.